So as promised, here are some examples. Example number one, alternate series error bound, right? We're going to figure out how far off we are. So here we have an alternating series. We know it's alternating because it's got -1 to the n plus 1. So each n is kind of alternating. It's getting positive, then negative, then positive, then negative. And we could add this up, right? We could add up these terms. And the question is, if we add them up, how close are we? Well, we don't know. We can't go to infinity. We could go out like a million terms and we'd be really, really, really close. But the question is, if I only wanted to go out, say, a few terms, how far off am I going to be? And that's what we're doing when we're looking at the alternating series error bound. So, I mean, let's just say we went out the first 4 terms, and we could look at the first 4 terms if we're in the mood, and why not? I'm in the mood. So the first term, 1, is going to be 1 over 2. The next term is going to be 2 over 4. We'll keep going, right? We're going to get 3 over 8, 4 over 16, right? Now, this is an alternating series. Notice that it is getting smaller eventually. You might say, wow, the 1/2, the -1/2, that's not good, right? That's not good. You're right. But remember, an alternating series is going to converge if eventually it starts approaching 0, and each term's magnitude gets smaller. And sure enough, this 2 to the n is going to get larger much faster than the n. So this is going to converge. At least, conditionally, it actually is going to converge absolutely as well, I think. But anyway, that's not what we're asking, right? We're asking about how far off are we? Well, these are 4 terms. And our sum of 4, I think that's just 1/8, right? Yeah. And we know that's not the actual sum, right? The actual infinite sum, if we went on, is going to be larger than this because we just went down, so the next one's going to go back up. So it's going to be larger than this. But how far off are we? Well, I don't know how far. I mean, I need to know the infinite sum to know how far off I am. But I can tell you that the maximum distance, the maximum magnitude that I'm off is the magnitude of the next term. So I can tell you, hey, 1/8 is not the right sum. It's some different number, but it's somewhat close. And how far is it? Well, I'm going to be off by less than, well, if I plug in 5, what do I get? Well, I get 5 over 32. So I'm going to be off by some number that's less than 5 over 32. So you say to yourself, well, is it 1/8? No, it's not 1/8, but it's 1/8 plus some number that's less than 5 over 32. And that's the kind of question that you're going to be asked, right? Oh, here are the first 4 numbers. What's the magnitude of the possible error? What's the largest error you could be off? And that's one problem. So that's something that you should be ready for. Let's now switch gears. We're going to talk about radius and intervals of convergence. So we're going to do this. So we have a series with an x in it, right? And we're going to talk a little bit more about why we have x's in our series soon when we start talking about power series. But for now, we're just going to figure out what values of x is going to let this converge, right? When are we going to have convergence for this series? So let's work it out. So as you can see, I jumped to the ratio test. Why did I jump to the ratio test? Well, whenever I have x, some kind of polynomial or some kind of like regular function like n to the 1/3 or 2, n or n squared or any kind of polynomial, and then I have some exponential function, that's my go-to. The ratio test is my go-to. So I forgot these. I'm going to forget these all the time. So you always need absolute value when you do the ratio test. So anyway, this is what it turns out to be. This here we know turns into a nice clean, I'll leave that up to you to see, this is the a sub n plus 1, this is a sub n, this is me just playing around with the fractions to kind of get things that cancel out over each other. This cube root of n over the cube root of n plus 1, we know the limit of that as n gets really, really large is 1, and this expression on the left just turns into this, right? Which therefore it's just this, right? Because there's no n in here, so it's just the absolute value of x minus 2. And we want this to actually what? We want this to converge. So in order for this to converge, we need this to be less than 1. And we love absolute values. This is so fun because we've learned how to do this for a long time. So we get this, right? And that's our interval of convergence. So our interval of convergence is from 1 to 3 for now, right? And we can figure out this width is 2. So if the width is 2, we know the radius of convergence is going to be 1, right? But we're not done, right? Why are we not done? Well, this interval of convergence is fine for now, but we need to test what's going on at 1, what's going on at 3. We can't assume that it's not going to work at 1 or not going to work at 3. Maybe there should be an equal sign here. We don't know. So let's jump, right? Let's jump ahead. All right, we just jumped. And what I did is I basically said, okay, we now need to test the endpoint. So we're now going to go into the scenarios where this expression, this initial expression that we had right up here, what happens if x equals 1 and what happens if x equals 3? So we have kind of two worlds, the x equals 1 world over here, the x equals 3 world over here. And we need to figure out if x equals 3 and if x equals 1, does this series converge or diverge? So if you plug in 3 here, you just get 1, right? And 1 to the n is just 1. Oh, that's cool. It's just 1, so it just becomes this. So let's look at this. Well, does this converge or diverge? Well, this is also another way of writing this, right? And do we remember our p-test, folks? What did the p-test say? Well, we have a p that equals 1/3, and it's less than 1. And do you remember, if we have less than 1, when you take the integral, remember what we did improper integrals? When you do 1/3, what happens when you take the integral? It pops up to the numerator, right? And if it pops up to the numerator, it goes to infinity, which isn't good, which means it diverges. Right, by the p-test. That's not good. What about this guy over here? Well, this guy's definitely not gonna. He's not gonna converge absolutely, right? Because this guy is diverging, so it's not gonna do it absolutely, but maybe conditionally, right? Well, it's an alternating series, so that's a good thing. If we look, the limit as n approaches infinity of this is actually 0, right? It's getting really, really small. As n gets really, really, really big, I mean, it takes a while to get really, really big because it's the cube root, but as it gets really big, 1 over that becomes 0, okay? And lastly, each term, at some point in the future, is each term less than the previous term? The answer is yeah, right? Because each time the denominator is getting bigger, so each term, as n gets larger, the fraction is getting a little smaller. So we have conditionally convergent. Because it's alternating, it converges. And that's why we get to come over here and change this interval. Happy, happy. And that's the correct interval of convergence, folks. Notice the 1 through 3 came from our doing our row and our ratio test, but testing the endpoints, we have to come up with both scenarios. So it's kind of like 3 problems, right? Well, sometimes it's a little bit easier than that. Sometimes you don't have to go through both endpoints nearly as long. You'll see that in a second. All right, we got another series. X plus 1 over 2, quantity to the n. Well, I'm going to go with my instincts. I see something to the n, I go to my instincts. Root test, right? And the root test says what we're going to do is we're going to find this row again, and we want it to be less than 1, just like the ratio test. And we're going to take the nth root of this. There needs to be a little absolute value in here too. That absolute value should be there, actually. Okay, so we're taking the absolute value, and no, I guess it doesn't really matter, actually, the absolute value going around. So we're going to get this, right? Because when you take the limit of this, the n's kind of cancel out. They go away, and you're just going to get this. And that makes sense, right? That's what the root test does. It kind of takes out the nth root and the power of n. They cancel each other out. And we want this to converge. We want this to be less than or equal to 1. So we get to do some absolute value work again, which is awesome. And now we know that our interval of convergence is that. Right? What's our radius of convergence? Well, the radius, this is 4 wide, right? And the radius is half of the width of the interval. So the radius of this is going to be 2. The radius of convergence is 2. That means if you're at the center, you go 2 to find the endpoints, basically. So if you're at the center, the center here is -1. You have to go 2 in each direction to get to the endpoint. Now, the cool thing is for this one, we actually don't have to do much more work to test the endpoints. Why? Well, if we plugged in -3, what are we going to get? Well, if we get a -3 here, it's actually going to be the same exact thing if we did the root test, right? And therefore, we're going to get -3 plus 1 over 2, and it's not going to be less than or equal to 1. It's actually going to equal 1. So you don't know. Oh, darn it, you don't know anything, do you? darn it, we do have to do more work. Remember, if rho equals 1 and you're doing the root test, you don't know it converges, you don't know it diverges, you have to do more work. All right, so I was wrong. We have more work to do. Hopefully this one won't be too bad. Well, yeah, what happens if we plug in -3? -3 plus 1 over 2. Oh, that's just going to be -1 to the n, right? So if we do that, we're going to get... Oh, that's just 1 minus 1 plus 1 minus 1 plus 1 minus 1. Hey, that is not... Those numbers aren't approaching 0. And guess what, folks? Either are these. And what did that divergence test, the very first test, tell us? Way back. The very first thing we did said what? That a series can only converge if the terms are approaching 0. So for both of these, the limit, I shouldn't write that way, the limit as n approaches infinity as of a sub n, so as n gets really large, what is a sub n approaching? Not 0 for both of these. So therefore they both diverge, which means that this is indeed our correct interval. Both endpoints don't work. Neither one of these are approaching 0. All right, so that's it for now. Enjoy. Talk to you folks later. Enjoy the problems that you're going to be doing.